In 1904, one runaway train raced downhill with nobody able to stop it. Its terrifying journey changed every train you ride today. The machine at the center was the railroad air brake system. It lets every car brake itself when pressure disappears. You meet it beneath passenger trains, freight trains, and subway cars. Before this system, a locomotive engineer controlled the engine brake. Brakemen had to climb between cars and turn handwheels. They watched for signals, guessed the timing, and hoped everyone reacted together. That was dangerous on a long downhill train. One delayed handwheel could leave several cars pushing forward. Then came the Westmoreland disaster near Greensburg, Pennsylvania, in 1904. A freight train began rolling backward down a grade. The crew tried handbrakes, but the train gathered speed. It smashed through a station and killed people nearby. The accident shocked America because the train had brakes. They simply depended on people reaching every car quickly. Engineer George Westinghouse had spent decades fighting that weakness. His answer used a continuous air pipe running underneath the train. A locomotive pump filled the pipe with compressed air. Each car carried a small brake cylinder and an air reservoir. When you pull the brake handle, the pressure changes inside that pipe. Valves on every car sense the change. They release air from each reservoir into its brake cylinder. That cylinder pushes a metal rod. The rod squeezes brake shoes against the wheels. Every car slows at nearly the same time, instead of waiting for a brakeman. Here is the clever part. Normal braking uses air pressure, but an emergency brake uses lost pressure. If the train separates, the pipe breaks open. Air escapes instantly, and every car applies its own brakes. The longer the train, the more powerful this safety idea becomes. But what nobody expected is a brake system could stop a train by braking itself. The visible pipe became a silent guardian beneath millions of wheels. Why does this work? Think of the train as a chain of small machines. Each car stores compressed air, like a charged battery waiting underneath its floor. The brake pipe tells every car when to act. A pressure drop opens a valve, and stored air pushes the cylinder forward. That movement becomes friction at the wheel. Friction is the one idea you can see. Hot brake shoes grip spinning wheels, turning motion into heat. The train loses speed without needing one giant brake at the locomotive. You have met this system when a passenger train stops smoothly at a platform. You may also hear its air compressor thumping before departure. On a freight train, the same principle protects hundreds of wheels and enormous loads. Listen near the cars, and you can hear air release during testing. Even subway trains use related pneumatic equipment, although modern computers often join the control system. The old safety logic still survives beneath the technology. The engineer who developed it faced years of skepticism. Westinghouse kept improving his valves after crashes proved that human timing was not enough. That 1904 Runaway did not invent the brake. It proved why railroads needed a brake that responded automatically, everywhere, at once. Today, a train can be longer than a skyscraper is tall. Yet one pressure change can command brakes across its entire length. That is the remarkable secret. The train carries its own emergency signal in a pipe. No radio, battery, or shouted order needs to reach each car. If you have watched a train stop, you have seen a century-old safety idea at work. Which machine should we investigate next? Like and subscribe for more engineering mysteries. And remember, the safest train is not the one with the strongest locomotive brake. It is the one where every car knows when danger begins. Thanks for watching the story of the 1904 Runaway Train. If you enjoyed it, smash that like button, subscribe for more amazing engineering stories, and drop a comment telling me what we should investigate next. See you in the next video.